Hello, Bobcats. Today I would like to talk about the hydrogen emission spectrum. Now, first off, let's look at a couple of pictures here to understand what we're talking about. You'll notice here that if we take normal light, incandescent light, or light from the sun, and we shine it through a focusing slit here and through a prism, we get a continuous spectrum, or a rainbow, where we have violet, indigo, blue, green, yellow, orange, and red. However, if we take a light bulb or a lamp or tube, gas tube with just hydrogen in it, and we put electricity through it, it makes light just like a tungsten does, or like our fluorescent lights do. And we focus that light through a slit, through a prism. We do not get the continuous spectrum. We get what's called a line spectrum. In other words, you see very specific lines at very specific wavelengths, 410 nanometers, 434 nanometers, 486 nanometers, and 656 nanometers. And each element, if you put a different element in a glass tube, vacuum glass tube, and put electricity through it, it will give its own type of line spectrum. So right now we're going to just look at hydrogen in a glass tube and the hydrogen spectrum, and discuss the hydrogen spectrum and how that will help us lead to the Bohr model of the atom. Now, before the Bohr model, that hydrogen spectrum had been observed, and let me write the hydrogen spectrum on here real quick for you. We have, let's say we have a red line here. This would be red, and it is at 656 nanometers. And let me bring this down closer so we can see better. There we go. And then that's nanometers, wavelength. And then we have the green line at about, not about, but at 486 nanometers wavelength. And a blue one over here. So blue at 434 nanometers wavelength. And then we'd have a violet at, and I'm going to put the violet above just because I'm running out of space down here, and that would be at 410 nanometers would be the violet one. So these are the four visual spectra lines for hydrogen. Now, a high school teacher named Balmer, who's a math teacher, had figured out an equation to explain these wavelengths using integers, and it's called the Rydberg equation. So let's look at the Rydberg equation. And it's 1 over wavelength is equal to a constant that he came up with, 6776 times 10 to the 7th inverse meters, and then you would take and multiply this number by 1 over an integer n squared. Let's say that's the final integer, minus 1 over the initial integer squared. So let's just look at violet for a second. And let's say violet, in this case, is an energy drop from energy level 6 to energy level 2 on the hydrogen atom. So I'm going to use a violet colored pen and go through the equation. So 1 over lambda is equal to 1.096776 times 10 to the 7th inverse meters times, well, let's say we drop from the 6th energy level to the second, so the final would be the second energy level squared minus the initial, which would be the sixth energy level squared. So that's 1 over lambda equals 1.096676 times 10 to the 7th meters. And then this would be 1 over 1/4 minus 1/36. And when I put these numbers in my calculator, I get 1 over lambda is equal to 2.43728 meters inverse. But remember, we're looking for lambda here. We are looking for lambda, and so I need to take the inverse of that. So lambda would be the inverse of 2.43728 meters. So the inverse of that would equal 4.10 times 10 to the negative 7th meters, which would convert to 410 nanometers. And so he was able to show that these wavelengths are a difference in these integers times this constant that he came up with. Well, later Bohr was able to use that and explain what was going on. They really didn't understand that there were energy level drops in the atom. He was just a mathematician that was able to relate differences in integers and come up with these values of wavelengths. And if you would like to, you could go through each one of those and determine that they all work out. But what Bohr did was he states that what's happening is that electrons exist in these energy levels. And it's the drop from one energy level to another that gives you the energy that is related to the wavelength. Okay, so let's look at what's going on here. So if I say that this is, let's say, here's my nucleus, and I have an energy level 1, an energy level 2, an energy level 3, 4, 5, 6, and 7. Okay, and these energy levels, Bohr gave them a principal quantum number, and that would be n. So n is equal to 1, n is equal to 2, n is equal to 3, and then I'm going to go on 4, 5, 6, and 7, and it can go on for infinity. And he says that if you take an electron, and you have an electron at the lower energy level here, let's say I have an electron here, so this would be at ground state. So I have an electron at the ground state, the lowest energy level, and I give it some energy. Either that energy can be through the electricity, through heat, whatever, but I give it energy. That electron absorbs that energy and will jump to a higher level, a higher energy state. Let's say it goes to this energy level state. So now at this higher energy level state, it's at an excited state. Well, it can't stay at the excited state. So at that excited state, from that excited state, it may drop to N3 or N2 or even N1. But let's just say it's dropping down to N2. So now the electron at this level drops to N2. And so there's an energy change there. It had to lose energy going from the N4 to N2. Now that energy is a very specific amount of energy that can be determined. And let's say in this case, the energy must be released as a quantum that has a quantum of energy that has a frequency and a wavelength, and that would be known as a photon. So we get a photon that leaves. So again, we have an electron in a ground state. It absorbs energy, gets excited to a higher energy level, which we call the excited state, and it drops back down. And it could drop to any energy level, but let's say in this case it dropped to energy level 2, and that change in energy, that energy difference from 4 to 2, has this wavelength, a frequency, a specific amount of energy known as a photon. Well, the equation for that is, we can say basically that we're looking at the change in energy is equal to energy from the high energy level minus the energy of the low energy level is equal to the energy given off as the photon. Well, we also know from Einstein's equation that the energy of a photon is equal to Planck's constant times frequency. So here we have that equation. And if you'll recognize it, we can say that the change in energy is equal to h times frequency, or Planck's constant times frequency. Well, Bohr also applied the Rydberg equation and said that we can take this change in energy is also equal to a constant, which is negative 2.18 times 10 to the negative 18 joules. Now this constant comes from, it's really h, which is Planck's constant, times the speed of light times this Rydberg constant. And I suggest you multiply h with its units times the speed of light with its units times this Rydberg constant and see if you get this value. And that value, you multiply it by the energy level drops or changes that occur. In this case, N, which is now the principal energy level, or principal quantum number for that energy level, squared, so we'll have final minus N, which is the principal energy level, squared of where it initially started. So if we look at where we're dropping from energy level 4 to energy level 2 in this case, let's see if we get something that matches from above. So I don't remember the color, so I'm just going to use green right now. So let's do E equals a negative 2.18 times 10 to the negative 18 joules minus, or times 1 over, now it dropped from energy level 4. In this case we're saying the energy change was energy level 4 to energy level 2. So 2 was the final, 2 squared minus 1 over 4 squared. So my delta E is equal to a negative 2.18 times 10 to the negative 18 joules. And that's 1/4 minus 1/16. So let me put that into the calculator right now, since I have done this kind of based on what I drew here. I didn't have the numbers predetermined, so that's so that's 1/4 minus 1/16 and that's 0.185 times a negative 2.18 second function EE negative 18, and I get a value of, this is the value I get. So that energy involved in that is a negative 4.09 times 10 to the negative 19th joules. Now, how do I know which one of these up here this correlates to? How do I know what energy correlates here? So remember the equation up here that delta E is equal to Planck's constant times frequency, but we can substitute frequency with C over lambda. So if I now do that equation, and let's see if we can get, we know that delta E is equal to HC over lambda. So lambda would equal HC over delta E. And I'm running out of space, and I may have to go to another page. I was hoping to get it all on this page. But what we have is 6.626 times 10 to the negative 34th joule seconds. The speed of light was 3.00 times 10 to the 8th meters per second. So my seconds cancel. And then my energy was, now the negative is because it's being emitted, so I'm just going to use a positive value here, times 10 to the negative 19th joules. Joules cancels, so that leaves meters. So my wavelength, I'm going to have to go to another page. So my wavelength here is equal to, and let me put it into the calculator, 6.626 second function EE negative 34 times 3 second function EE 8 divided by 4.09 second function EE negative 19, enter, and that comes out to be 4.86 times 10 to the negative 7th meters, which when I convert that, remember 1 meter is 10 to the 9th nanometers. That'll come out to be 486 nanometers. Now that value, if we look back, that value is this equation, this value right here. Oops, excuse me. So this line spectrum correlates to this energy change from an electron dropping from an excited state to a lower energy state and emitting that amount of energy as a certain wavelength and frequency that we can determine from this equation and then relate it back to either frequency or wavelength because we know this energy now, and it comes out to be the 486 nanometers. So using those equations, we can show where the electromagnetic spectrum or those line spectrum come from. So let's look at the Bohr model for just a second, or discuss the Bohr model. And with the Bohr model, what we say with the Bohr model is, so Bohr, what he discussed was he figured out that electrons exist in very the specific energy levels around the nucleus that these energy levels have a principal quantum number. So there's principal number N indicates energy levels that the electrons exist in. And that when you have when electrons move from one energy level to another, so when there's energy level changes, so let me see how I want to say that. As an electron, or the light spectrum the emission spectrum that we see with elements occurs when excited electrons drop to lower energy levels emitting a specific amount of energy, or a quanta of energy. Quantum of energy known as photon. So, what we see with all of this is that when I look at, we can discuss now how the electromagnetic spectrum is produced by this excitation and dropping to lower energy levels of an electron. When I look at this again, I can show you using the energy levels. So if we have energy level 1, energy level 2, energy level 3, energy level 4, and yes, the energy levels get closer together the further they get from the nucleus. So that's 1, 2, 3, 4, 5, 6, 7. Okay, so we have n equals 1, n equals 2, n equals 3, n equals 4, and then we have 5, 6, and 7 up here. Okay, so what we do know is that when electrons drop from any excited state to energy level 2, so they can drop from any excited state to energy level 2, then this is called the visible spectrum, and it's called the Balmer Series. So our visible light comes from electrons dropping from excited energy levels to energy level 2. If they drop from energy level, any excited energy level to energy level 1, so we can drop from any excited energy level to energy level 1, and I'm just showing 3 of the drops, it could be anything. When they drop to energy level 1, that's ultraviolet light, and it's called the Lyman Series. And yes, your hydrogen will do the same thing. It's not just doing visible light, it's doing ultraviolet. And if they drop from energy level, any excited energy level to energy level 3, then that's infrared or IR spectra, and it's called the Paschen Series. Or Paschen Series. And so you can think that if you're dropping to energy level 4, that would be microwaves, energy level 5, radio waves, and so forth. And the thing is, the higher energy comes from, most of the time will come from the nucleus. So if this is my nucleus down here, during radioactivity or radiation, you'll get X-rays and gamma rays. Okay, so our visible spectrum, or our electromagnetic spectrum, comes from the fact that electrons get excited and drop to lower energy levels. And we can figure out any of those using the equations delta E equals H times frequency, blank, delta E equals HC lambda, and delta E equals this negative 2.18 times 10 to the negative 18th joules, 1 over N, which is the energy level, squared final, minus 1 over N squared initial. And just to remind you, if you get a negative delta E, that means it's emitted energy, and if it's a positive delta E, it is absorbed energy. And that is the Bohr model, and how we came up with the Bohr model in a nutshell. And I hope this is helpful for you in understanding the hydrogen emission spectra. Thank you very much.